Okay, in this lecture, we will focus on the stiffness analysis of beam, right? In previous lectures, we have done a strength analysis of beam in bending when we are when we are studying bending of beam, right? What we have done there, beam in that analysis, the requirement for the beam is that beam should be able to resist shear stresses, bending stresses, and bending moment, right? And analysis parameters in that case was shear stress, maximum bending stresses, or maximum normal stresses, maximum shear stresses, and maximum bending moment. They are the analysis parameters, right? But here in stiffness analysis, what we do here, beam should be stiff enough not to deflect more than the permissible limit, right? It stiff enough not to deflect more than the permissible limit means, suppose this is our beam, right? This is our beam. When we apply load, when you put a load on its center, then it will deflect, right? There will be sagging bending, or when we apply load at the end and one end is fixed, then there will be hogging bending. Then what we see that it deflect from its original position, right? Say original position is straight line, and when it is deflected, there is a curvature line, right? It is deflected. Then this deflection from initial straight line must be within permissible limit, right? It should not be beyond this limit, because when it goes beyond this limit, there will be fracture in the material. And this happening we basically see in our roof beams or joist, right? When there is the deflection in the beam or joist, there will be some cracks appears on the ceilings, right? On the plaster of the ceilings, or joist, clear? On the plaster of the ceilings or floors, right? There will be cracks. So analysis parameters are here, the deflection and slope. I have made a diagram of deflection of beam. Say here, this is your beam without load, right? This is the beam without load. It is a straight member now, right? And this red dotted line showing the neutral layer line, clear? When it is loaded, we place the load W at the center, right? This neutral layer line gets a curvature shape. Now it is known as elastic curve, right? When this neutral layer line is changed into a curvature form due to the deflection, then it is elastic curve line, right? Clear? Here I have written it. This is the neutral layer line, unloaded neutral layer line, and when load is applied on the beam, then this one is elastic curve line. This is elastic curve line, and this is showing here the deflection is maximum at the center when beam is simply supported, right? Then and subjected to center load, right? Then there is the maximum deflection at its center, Y max. So beam must be stiff enough to allow deflection within permissible limit. That this Y max should be within permissible limit, right? This is the main objective of this unit, that we will calculate the value of Y maximum for each loading conditions, right? And what is the slope? When beam is taking curvature shape, suppose here is a point A, right? When we draw a straight line, at point A, also we see the tangent line at this point, then what we see that this line from the initial straight line makes an angle, right? Makes an angle in anti-clockwise direction. Say this is initial straight line, then here is the angle here. This is the slope of this curvature, right? And at this point there will be no slope, because here when we draw a tangent, right, then this tangent line is parallel to the initial straight line, right? This unloaded neutral layer line. So there will be then the slope will be 0. For maximum deflection, what we see, there is a slope 0. But here at a start point, when you draw, say here is a point A, when we draw a tangent here, right, then angle from the initial straight line is theta, right? This is the slope. This is the slope. Clear? Now we will discuss a relation between slope, deflection and radius of curvature. Clear? Relation between slope, deflection and radius of curvature. See, this is in previous I have made. Consider a very small portion of this beam, right? This is beam of AB of length ds. When it is curved, when it is changed, when it is loaded, then the curved portion is now this A dash B dash, how we see AB, right? We are getting this portion under analysis, right? So this is a very small element, right? So this portion is very small and length of this portion is ds. This is the arc, right? And tangent at A makes an angle alpha, tangent at B makes an angle alpha plus d alpha. Clear? And when we draw a radius line at this point A and B, they meet at a center C, right? This is the arc center, right? This is the center of this curvature, and radius or curvature for this curve is R, right? From geometry, what we will find that if this angle is alpha and this is alpha plus d alpha, then this angle will be d alpha, right? And horizontally, we make a triangle, right angle triangle. That, right? This is distance of B, horizontal distance of V from A, and vertical distance of B from A is dy, horizontal distance from A is dx, right? And slope will be equal to the tangent of this dy upon dx. Clear? Now from geometry, what we see, this angle ACB is equal to d alpha. This angle ACB is equal to d alpha, and ds will be equal to rd alpha, right? ds will be equal to rd alpha. Already we know that arc length is equal to the radius and angle subtended by arc length, right? Now what we can write, 1 by r equal to d alpha upon ds. If we assume that because length of arc is very small, this portion AB is very small of the beam, a small segment of the beam, then AB, this ds will be equal to the dx. We say it, right? We have assumed it. Then 1 by r will be equal to d alpha upon dx. Clear? Now if we consider triangle ABP, this is the triangle, this is the point P. Consider triangle ABP, right? Then what we will find, this is alpha, then this angle will be also alpha, then tan alpha will be dy by dx. So I have written here, tan alpha is equal to dy upon dx, that is equal to the slope, and alpha is tending to 0, right? If curvature is very small, then it basically we can assume it as straight line, right? Then alpha will be very small. When alpha is tending to 0, then tan alpha equal to alpha, right? And this alpha will be equal to dy by dx. Differentiate it again, then what will we find? D alpha upon dx equal to d2y upon dx2. Now d alpha upon dx is equal to 1 by r. Put this value into this equation, then 1 by r is equal to the d2y upon dx2, right? Now from bending equation we know that m upon I is equal to E upon r, right? Then m equal to EI into 1 by r, and 1 by r is equal to d2y by dx2. Then I put it here. Then m equal to EI upon d2y upon dx2. Then what we see, that this deflection y is largely depend on the bending moment acting on the beam, right? Here we have neglected the effect of shearing load, because effect of shearing load is very of negligible amount during the stiffness analysis of the beam, right? In this lecture we will discuss it. We have discussed the relation between slope, deflection and radius of curvature, right? There are sign convention of measuring this y, right? Whenever y will be below this unloaded neutral layer line, then y will be negative. Say when y will be negative y-axis, then be negative, and when it will be along the positive y-axis, then it will be positive. Y, right? Say this is our neutral line. When it will be measured, will be in downward direction, then it will be negative. When it will be in upward direction, it will be positive. And x, we know that positive x-axis. General rule, we will follow the sign convention rule generally which we adopt for xy axis. Then x will be measured here positive, and here it will be measured negative. Bending moment, we know that bending moment during sagging, bending moment is positive. During sagging, bending moment is positive, or during hogging, bending moment is negative. These are the sign convention which we will adopt during the analysis of deflection of beam. Clear? In this lecture, this is all about the deflection. Further we will study the deflection methods.